Alright, so let's take a look at that alarm code for the code we just ran with the two alarm clocks, and just kind of see an example of how this stuff plays out in Macro-11. So basically, front panel switches and LEDs are available at this address. Here's the three addresses for talking to the PigBus, so the slot register, the command and status register, and the data register. Here's where we set up the interrupt handler. So at location 140, that's where the PigBus vectors, we list handler, which is going to be replaced with the address of whatever label handler is. That's going to be our interrupt handler. And then a word of 200, which sets the interrupt priority level to 4. And then I'm going to jump to location 1000 and have a label start, and that's going to be where I declare the beginning of the program. We put that nice high value into the stack pointer, and then same thing that we did with the interactive commands through the simulator. We talk to slot 0 and hit bit 0 of the command status register. That turns on global interrupts. The alarm is device 4, so we go ahead and we move device 4 into slot 1, so that puts one alarm into the PigBus. We move decimal 1000 to the data register, and then move 11 into the CSR. Remember this, this first one says load the data register as your period value, and then the second one says turn on interrupts. And then we interrogate bit 1 of the CSR to make sure that this command has been processed. Basically, when we do this move, we're talking to the alarm clock and saying, hey, I want you to load in the value from the data register and also enable interrupts. We don't want to do anything like change the data register until that's been accomplished. And it's asynchronous, right? The alarm clock is a separate process. So we poll bit 1 of the command status register, waiting for it to clear. And once it's equal to 0, once it's cleared, we know that the device has finished processing our instruction, and now we can move on. So now we load device 4, that's the alarm clock, into slot 2. So we've got a second alarm clock loaded. And then we initialize some registers. So R0 is going to count, is going to remember what the switch position is so we can detect when the switches change. R1 is going to count how many 1-second interrupts we've gotten, and R2 will count how many of the variable interrupts we've gotten. And then we go into a main loop, and most of the time we're just sitting right here. We're looking at the switch position, seeing if it's changed from R0. If not, we go back and we just hang out, right? So if they're equal. Once they change, that means we want to change what's in this second alarm clock's period register. So first we save the switches into R0 so that we know when they change again. We go back and we put a 2 into the slot register. We don't need to specify the device here because the device has already been plugged in. We could put a 402, but we can just put in a 2 to say talk to slot 2. Take the value on the switches, load that into the data register, and then again move 11 into the command status register, which says load whatever we put in the data register into your internal period register and enable interrupts. Wait for that to finish, so check bit 1 of command status, wait till it's clear, and then go back to our loop. So most of the time we're just sitting here. When you flip the switch, we run through this little bit of code which loads a new value into the second clock's period register and then goes back. That's our whole program, so we're just sitting here in this tight loop, branching to ourselves. But when an interrupt occurs, remember up in location 140, we said go ahead and store the address of handler. Well, handler is a location right here. So this is the code that's going to get run when we get an interrupt. So we put a 0 in the slot register, that's the PigBus controller. And once we do that, the data register is loaded with the address, the slot number of the interrupting device. So we can look in the data register and see if it's equal to 1. And this happens immediately, right? So when we write to the Unibus, we won't come back from this this move instruction until the data register has been updated. So we don't need to synchronize with a register to check and see if the device is finished. This is handled by the controller itself. So we talk to the controller, and as soon as we do that, it will put the address of the last interrupting device into the data register. We can see if that's device 1. If it is, we know that the 1 second interrupter just triggered, and so we'll come down here, increment R1. Otherwise, it had to be the second alarm clock, so we'll increment R2 and then skip down to display. And then display just displays those two counts, R1 and R2, into the 2 bytes on the display. So we take R1, put it into R3, swap that over to the left, and then add R2, so R2 takes in the lower 8 bits, move that composite into the LEDs, and then return from interrupt. So that's the whole system, right? And our interactions with the alarm devices are pretty simple. It's mostly just working through the data and CSR registers, and since we have 2 devices, playing around with the slot register also. So that's an example of writing assembly language to use a pre-existing device. The next part of this is looking at how we actually create one of these devices, what goes into making, for example, the alarm clock device. And rather than work with the alarm clock initially, which is a somewhat more complex device, let's just write a new device completely from scratch. Let's make an adder device.